Hi, let us continue our discussions on sequence and series with the geometric series. A geometric series is defined as the sum of the numbers in a geometric progression. Using the sigma symbol, which stands in mathematical language for the sum of, we can write a finite geometric series as the sum of j is equal to 0 to n minus 1 ar to the power of j, that is equal to ar to the 0 plus ar1 plus ar squared, and so on until we reach ar to the n minus 1. This equation just implements the basic definition of a geometric series. Let us now find a simple formula for finding a geometric series. Let us have a geometric progression with elements, total number of elements equal to n. That is our geometric progression. We then start with this basic equation that we defined, which this equation is based on a basic definition. Then let's just repeat this equation. We say the sum of j equal to 0 to n minus 1 ar to the power of j is equal to ar to the power of 0 plus ar to the power of 1 plus ar to the power of n minus 1. Let us multiply both sides of this equation by the term 1 minus r, where r is the common ratio of our geometric progression. And we do the same on the right hand side of this equation. Let us multiply this equation out on the right hand side. It's pretty easy to do. 1 multiplied by all these terms simply gives us these terms again, plus ar to the n minus 1. Then the second term is then given by multiplying minus r with all these terms here, so it's easy to write down. So it's minus r to the power of 1, because we multiply by r, minus ar squared, minus until we reach ar minus ar to the power of n. If we now, what we can easily see here, we are left with ar to the power of 0, but ar to the power of 1 is deleted because we subtract ar to the power of 1, and we are left with ar to the power of 0 minus ar to the power of n. Now we can just simplify this as follows. This is equal to a times 1 minus r to the power of n. Therefore, we can write the following. We can thus write Sn, which is the sum of this specific geometric sequence, which gives us the geometric series, is equal to the sum of j is equal to 0 to n minus 1 of ar to the power of j is then equal to a multiplied by 1 minus r to the power of n divided by 1 minus r, on the proviso that r can never be equal to 1, because if r is equal to 1 we will divide by 0, and that's an invalid mathematical execution. Okay, so therefore this equation can also be written as Sn is equal to the sum of I is equal to 1 to n to the power of ar to the I minus 1. That's equal to a multiplied by 1 minus r to the power of n divided by 1 minus r, and again r can never be equal to 1. These equations are precisely the same equations, actually just written in a different method. Okay, now let us apply a geometric series to an exam example. The exam example, the examiner gives us, what he asks us to do is, the examiner says find the smallest number n for which the first n terms of for which the first n terms is. In other words, he gives us a geometric series. He defines it to be a geometric sequence rather, and he gives the sequence as 1, 1.1, 1.21, 1.331, and so on. He gives us this geometric series, and he says find the smallest number n for which the first m turns is a sum greater than 70. So in summary, what does the examiner do? He gives us this geometric series, and he says how many terms, find the first n terms where the geometric series will be just larger than 70. So he gives us this geometric progression, and he wants us to find a geometric series but limited to n terms, where the n terms will give us a value just greater than 70. For the given sequence, obviously we have a is equal to 1. That is just logical. That's the first value in the geometric progression. And we can obviously see where r is the common ratio. If we look at the first two terms, we can easily deduce that the common ratio is 1.1, because the common ratio is defined by the second term divided by the first term, and 1.1 divided by 1 is 1.1. So we have the common ratio as 1.1. If we now look at our basic implementation of our basic formula of a geometric series, this is the basic formula of a geometric series. We can just repeat it here. We say the basic formula for a geometric series is equal to a, which is the first term, multiplied by 1 minus r, where r is the common ratio of the geometric progression, to the power of n, divided by 1 minus r, as long as r is not equal to 1. Then we can simply substitute for the values of a, which is 1, and r, which is 1.1. A very simple substitution, and this then leads to 1 multiplied by 1 minus 1.1 to the power of n, divided by 1 minus 1.1. And if we simplify this, we have 1 minus 1.1 to the power of n, divided by minus 0.1. And thus we can say that Sn is equal to 10, which because 1 over 0.1 is equal to 10, and we have a sign change here, so that'll be 1.1 to the power of n, because this sign change will change the signs of both these terms on top of the equation at the numerator of the equation of this right side of the equation, minus 1. Okay, now given Sn, the examiner tells us for what n will Sn be larger than 70. This implies that 10 multiplied by 1.1 to the power of n minus 1 must be larger than 70. Therefore, 1.1 to the power of n must be larger than 8. How did I get that? I just divided this left-hand side of the equation by 10. I must do the same on the right-hand side, which gives me a 7. If I add 1 to the left-hand side of the equation, I must add 1 to the right-hand side of the equation. And that leads me to say that 1.1 to the power of n must be larger than 8. Now, the basic definition of a logarithm, if I, for the time being, just state, okay, 1.1 to the power of n is equal to 8. The basic definition of a logarithm states that the value of n is equal to the logarithm of 8 to the base of 1.1, where 1.1 is the base of this exponential value here. Then I can use the basic laws of logarithms. I can say this is the log of 8 to the base of 10 divided by the logarithm of 1.1 to the base of 10. Now I can use my calculator to calculate the value of 8, of the logarithm of 8 to the base of 10, and the logarithm of 1.1 to the base of 10, and I will find this to be 21.82. So for n, that implies for n larger than 21.82, the sum of the series of our given geometric progression will be 7 larger than 70. So the smallest natural number n, for which the geometric series will be larger than 70, will be equal to 22. And that is the answer that the examiner is looking for.